the resistance to it correlate with the production of gamma interferon and development of T helper 1 stimulation. And effective treatment and vaccination of the leishmania is biased towards T helper 2 response, which is the humoral immunity. And as you know, the destruction of the tissue and the skin and the soft tissue due to leishmania is due to activation of the cell-mediated immunity and the macrophage and the gamma interferon release, which is lead to destruction of the soft tissue and with the scar on the skin. While immune response to the worms elements and the best examples, Schistosoma mansoni that causes bilharzia, and the egg stimulate the delayed type hypersensitivity, lead to granuloma formation when the female of schistosoma laid its egg in the wall of the bladder, lead to formation of egg granuloma, while the worm can evade the immune response by decrease the expression of the antigen on its cell surface and enclosed itself with the glycolipid coat mask to mask that's mask its own antigen, so the immune response did not recognize it, and the immune response to it stimulate T helper 2 with high titer of the IgE that increase in degranulation of mast cell and influx of eosinophil, then bind to antibody-coated worms, inducing degranulation and death of the parasite via the ADCC, antibody-dependent cell-mediated cytotoxicity. So here it's type 1 hypersensitivity reaction due to stimulation and production of the IgE antibody. Now another pathogen is the fungal infection. The innate immunity is the first barrier neutrophil, which is a strong defense against it, and toll-like receptor, complement receptor, and normal flora inhibit the fungal growth. And the cell, if the innate immunity fails to eradicate the fungus, so the cell-mediated immune response will act against the fungal infection and stimulate the T helper 1 cell with gamma interferon production and with formation granuloma, and the fungi remain dormant inside it. And nowadays they found that T helper 17 had a regulatory role in controlling the adaptive immunity that helped T helper 1 cell and discourage T helper 2. And fungi produce capsule to evade the immune response and expulsion from the macrophage. Now we have the new subject, which is called vaccines. Vaccines. This is a back history of the vaccine, which is developed by the English physicians Edward Jenner in 1798, made a giant advance in the development of the immunity when he found that the milk mates that deal with the infected cows with the cowpox, so they get immunized from this virus. So the Edward Jenner used the fluid in the pasture of these cowpox and start to immunize the population against this cowpox. And later on, Louis Pasteur worked on fowl cholera and proved that aging had weakened the virulence of the pathogen. So vaccination is an attempt to induce immunity intentionally. And vaccine from the Latin word vacca, which is mean cow, due to the cowpox in honor of Edward Jenner's work with cowpox inoculation. How can we design vaccine for active immunization? Vaccination educates the adaptive immunity system, preparing it to deal effectively with pathogens not readily eliminated by innate immunity, and know the branch of the immune system that is activated, the humoral or cellular, and third, development of the immunologic memory. So when we design a vaccine, we must educate the adaptive immunity, and second, we know which type of the immune response to this pathogen, if it is humoral or it's a cellular. So every pathogen stimulates the humoral immunity, So I design a vaccine that stimulates the human immune response. While if the pathogen stimulates cell-mediated immunity, so I design a vaccine that stimulates the cell-mediated immunity, and not vice versa. And my vaccine, I must design vaccine that induce immunologic memory. So a vaccine without immunologic memory, so it's of no benefit. So these three factors must be put in mind in order to design a vaccine for active immunization. Types of vaccine. First, we have live attenuated vaccine. And some microorganisms can be attenuated, so they lost their ability to cause significant disease pathogenicity, but retain their capacity for transient growth within an inoculated host. And the attenuation can be achieved by growing a pathogen for prolonged periods under abnormal culture condition. For example, the bacteria that grow at 37 centigrade, which is the temperature of the body, and allow these bacteria to grow at 40 centigrade. So this bacteria that grow at 40 centigrade used as a vaccine. Second, attenuated strain of Mycobacterium bovis, which is called Bacillus calmette-guerin, BCG, stimulate the cell-mediated immunity and used in vaccination against TB and measles, mumps, rubella, MMR, and the polio. Sabin vaccine consists of 3 attenuated strains of polio, and this is orally given and stimulates the secretory IgA in the intestine because it is fecal-oral transmission, and we must stimulate the immunity in the intestine by production of secretory IgA. So give the vaccine orally. And this is Sabin vaccine, which is live attenuated strain of the polio, include 3 strains of the polio virus. And this live attenuated not give it to the immune suppressed patient because this leads to infection with polio virus. A second type of vaccine, inactivated or cold vaccine, and this can be achieved by the heat or chemicals like formalin, and pathogen is not capable of replicate, but it retains its antigenicity. Heat inactivation is often unsatisfactory because it causes extensive damage to the protein, and as we know that the most potent antigen is a protein, so when we use heat to inactivate the pathogen, so kill the protein and so we denaturate the protein and it's become of no benefit. And this is like a cholera, a polio, which is called the Salk vaccine, and the rabies. And here, a polio Salk vaccine, which is killed, give it to patients with immune suppression because the virus is killed and not induce infection. The differences between or the advantages of the live attenuated vaccine induce a strong immune response because it's cause subclinical infection, and this is give lifelong immunity and give it single dose as a TB, as a tuberculosis BCG for used for tuberculosis vaccine, give it only single dose first week of life. While the disadvantage of live attenuated requires refrigerator storage and we do not have electricity, so this is a major problem. And many may mutated to virulent form and may be associated with complications similar to those seen in natural infection. For example, measles vaccine may cause complications like encephalitis. While the advantage of a cold vaccine, stable, safer, not need refrigeration, so no need whether there is electricity or not. And disadvantage, weaker immune response require booster dose, and as we know that the vaccine given at 2 months, 4 months, 6 months, which is called booster dose, and less effective in inducing cell-mediated immunity, and not all pathogens will be killed by the chemicals. Another type of vaccine, which is called toxoid vaccines, And here use bacterial products that some bacteria produce toxin, exotoxin, and we use this toxin and we use this toxin and inactivated by formalin to form what's called toxoid, and this lead to formation of anti-toxoid antibodies. The best example is diphtheria and tetanus, and the immune system are primed to recognize bacterial toxin. And diseases in those exposed to tetanus can be prevented by treatment with tetanus antitoxin. Another type of vaccine, subunit vaccine, consists of specific purified molecules from derived from the pathogen like bacterial polysaccharide capsule. For example, Streptococcus pneumoniae consists of 23 antigenically different capsular polysaccharides, and this vaccine induces formation of opsonizing antibody. Another example, Neisseria meningitis. Another type of vaccine, conjugate vaccine. Here, certain bacteria have polysaccharide that coats the bacteria, and this is poorly immunogenic, and so link it with another protein, which is, for example, toxin, to induce the immune system, and then the immune system will recognize the polysaccharide as if it is were protein antigen. This approach is used in the Haemophilus influenza sorry, Haemophilus influenza type B vaccine. Recombinant vaccine. Here we start to use the genetic engineering techniques to provide a way to attenuate a virus by selectively removing genes that are necessary for the virulence, and only select the genes that are responsible for the antigenicity. And the basis of these new vaccines is the identification of proteins of the infectious agents that are able to induce an immune response in similar way to that produced by the whole agent. Using genetic engineering, the genes coding for those proteins can be selected and then cloned in the plasmid and then expressed using different vectors like bacteria or yeast. Bacteria like E. coli or yeast, or mammalian cells using recombinant DNA technology. And the best example is the hepatitis B vaccine. The another type of vaccine, DNA vaccine, which is created from infectious agent DNA. It works by insertion of viral or bacterial DNA into a human cell. Some cells of the immune system that recognize the proteins expressed will mount and attack against these proteins and cells expressing them. Because these cells live for a very long time, if the pathogen that normally express these proteins is encountered at a later time, they will be attacked instantly by the immune system. And this type of DNA vaccination is still experimental. And thank you.